Hello everyone. Today let's talk about finding the general antiderivative of the function x to the n. This is actually just a power function. There are two different cases when we're finding the antiderivative for this x to the n. One case is that when n can be any number, real number except negative 1. And so what do? We are going to use the general power rule, but we are going to reverse it this time. Okay, so how do we do that? Let's just think about this. Let's say we have, let's look at a few examples and see what the pattern is regarding reversing the general power rule. So let's think about this. We have, for example, let's say we have a function, okay? So so this is more like scratch work or something. So let's check. Let's do some scratch work on the side here. Okay, so let's say we have a function that's y equals x to the fifth, for example. Okay, so what's going on here? We are going to take its derivative, and then its derivative is going to be what? Y prime, okay? And that's bringing down the phi to the front, and then we are going to subtract 1 from our power. So as you can see here. Now, our goal here is to go backward because we are finding the antiderivative of the phi x to the fourth. Then we are going to get x to the fifth. And of course, we already know the answer of the antiderivative for phi x to the fourth because we actually got this answer by differentiating x to the fifth. But the problem is, how do we go backward easily? Think about this. One thing that we observe is that we have what? We have a 4 right here. And then when we go back to the original function, when we find antiderivative, we're actually going to add 1 to our power. So to go from the 4 to the 5, we actually would be doing what? We are adding 1 to it. And actually, if you do a few more problems, you can see that this pattern, it's always going to be the same, except that when n is equal to negative 1, then it will be a different case. But as you can see here, we are just adding 1. So let's just do one more and then you can see that okay, so we're just always adding 1. Let's try another one. Let's say it's x to the I don't know, maybe we can do a square root, so x to the 1/2. And then when we take the derivative, we are going to get y prime. That's equal to what? You bring down the 1/2 and then you subtract 1 from the 1/2, which is negative 1/2. Do you see what's going on here? When we go from negative 1/2 and then we get to the 1/2, we are adding 1, right? So now one thing that we need to just keep in mind is that when we find the general antiderivative using or by reversing the power rule, we are going to add 1 to our exponent. And then you may say, what about the coefficient in the front? We will worry about that later, but regarding the power, we are going to just add 1, okay? So as you can see here, the 4 becomes the 5, okay, by adding 1. And then same thing here, the negative 1/2, and then it becomes the 1/2, positive 1/2, by adding 1. Yeah, so this would be something that we can apply to our n power right here, okay? And then you may say, now, what about the number in the front, right? So we have a 5 right here, but then when we go back, we actually have a coefficient of the 1. Same thing here, we have a 1/2 right here, but then once we go back, then we are going to have a coefficient of 1. The question is, how do we see that kind of relation? Like what's going on here? What actually is happening here? Now we actually want to think about what happens when my y prime, okay, so let's come up with a different question right now. So let's say we have a y prime of, now I don't want the phi in the front, okay, so I don't really want the phi in here. I just want to, let's say, find the antiderivative of x to the fourth. Now this problem looks more like the problem that we are looking at right now because the coefficient for the function that we have, it's just a 1, right? So now if I have a coefficient of 1 here, then I'm not going to get my antiderivative to be x to the fifth, because when we differentiate x to the fifth, we are supposed to be getting a phi in the front, but then we don't have a 5 right here, so that doesn't work. So now how do we go backward? we already know that when we go backward, okay, so that looks a little bit weird when I try to draw the arrow. Okay, now I think that works. So if we go backward and then we try to come up with that, what is that? We try to come up with using the rule that or the pattern that we observe right here, we are going to add 1. So it's guaranteed that we are going to get what? X to the 5th, right? Because we're adding 1 to it. So that's no problem for sure. Now the question is, how do we get rid of the 5? And then we can actually, how do we go from 5x to the 4th to x to the 4th? We can actually just multiply this by 1/5. And then we can do that. So what's really happening here is that if we go from 5x to the 4th and then we want to go from there to x to the 4th without the 5 in the front, we can simply just multiply that by 1/5. And then do you see what actually is happening right here? We also need to do the same for the original function, the y, right? So that means from here, we will need to multiply by the 1/5 times the 1/5. And then so what happens? We are going to put a 1/5 in the front. And then you may say, does that even work? When we do that, yes, it's going to work, as you can see here. Let's try to differentiate this function and see what's going on. So when you differentiate this function, remember that according to the constant multiple rule, we are not going to be doing anything to this 1/5. So when we take the derivative of this function, now what happens? We keep the 1/5. And then we are going to be just differentiating x to the 5th. Yeah, so we keep the 1/5 in the front. And then we differentiate x to the 5th. Now what's going on here? When we differentiate, we are going to get 1/5, right? That's being kept in the front. And then when we differentiate this x to the 5th, we are going to get 5x to the 4th. You see what's going on here? Because we multiply 1/5 by the x to the 5th, so that when we differentiate 1/5 x to the 5th, this 5, it's going to cancel with this 1/5 right here. So now that we get cancel. And then so what do we get here? So we are actually getting this x to the 4th. Now, according to this pattern right here, then what do you see here? There is, how can you relate this 1/5 with this exponent that we are getting here? Do you see that they have the same, this denominator is the exact same number as the exponent that we have here, or we call this the new exponent, right? The original exponent is the 4th, right? When we go backward, we are going to get a new exponent by adding 1. So we are getting the 5 here. And then this 5 is actually just the same number as our denominator here. And so what's going on here? We are going to just do 1 divided by this new power. And we should really just think of it as multiplying this function by the reciprocal of the new power. Then we have our antiderivative. And this works for any power function when n is not equal to -1. So now the general formula for finding the antiderivative of this function, we usually use capital F to denote the antiderivative of lowercase f. Okay, and then so what's going on here based on whatever scratch work or whatever pattern that we observe right here. So first we are going to add 1 to our original exponent. So in this case, we are going to put x and then we add 1 to the exponent. See what's going on here? We added the 1 to the n. So now that becomes our new power. So if that's a 4, we are going to get 5. That's a -1/2, then we are going to get +1/2. So whatever n is, we are going to add 1 to it. Is that okay? And then do you see that I left some space in front of the x? That's actually important because we need to make the adjustment so that we can multiply by some number in the front of our power function so that we can cancel out any number that when we differentiate, we can cancel out with whatever power that we bring down to the front when we differentiate. So what is that coefficient that we need to put in here? According to the pattern that we observe here, then what happens? We are going to multiply by the reciprocal of whatever power that we have because we're taking 1 divided by this number. Okay, so that's really just the reciprocal, the n plus 1. So what do? We can do 1 over, that's reciprocal, right? So 1 over, and what do we get here? N, and then plus 1. And then, of course, because we're finding the general antiderivative, we can actually add any constant that we want in this case. Because whenever we differentiate a constant, we are we are going to get a 0. So when we differentiate this function, we are going to get f, which is x to the n. And then without adding any other stuff, because the c will disappear when we differentiate it. Okay, so that's the general antiderivative for x to the n when n is not equal to -1. Let's see a few examples down here so you can see what's going on. So let's try one example. We're getting using this general formula. Let's say we have f of x is equal to x to the 7. So what do we do when we want to find the antiderivative? We are first going to leave some space in the front, right? So leave some space right here, and then we can put x to the, now add 1 to the 7, so that we are going to get 8. And then now we need to multiply by the reciprocal of this 8, which is 1 over 8. Its reciprocal is 1 over 8, so we put the 1 over 8 in the front. So that's why I asked you to leave some space, because we gotta multiply this x to the 8 by some number. And then, of course, we can put the constant. Okay, so that's pretty easy, right? One thing that I really want to point out is that when we do this, make sure that you add the 1 to the power first. Once you obtain the power, then you are going to multiply by its reciprocal for the function. So the order is important. We have to add 1 to the power first before we multiply by the reciprocal. So we cannot multiply by the reciprocal of the original power and then add the 1. That's not going to work. Okay, let's try another example. Let's say our function is 1 over x cubed. Then you may say, that doesn't look like x to the n. It's not in the right form, right? So that's correct. That's not in the right form. So to reverse the power rule, we actually need to rewrite this as x to some power. And to do that, then we can actually use negative exponents. So we have x to the -3. Okay, now as long as this exponent is not equal to -1, then we can apply this formula right here. So our antiderivative is going to be what? So again, leave some space in the front. And then now we write it down as what? X to the, if you add 1, what do we get? -3 plus 1, which is -2. Is everyone okay with adding 1 to a -3? That's good, right? And then we need to multiply by the reciprocal of this -2, which is what? -1 over 2. Remember, when you take the reciprocal of a number, the sign does not change. If it's initially negative, then it should still be a negative number, but then you now have the reciprocal. Okay, and then what do we have here as the constant? Well, just the constant, right? So just put plus c. So that's good. And then actually, let me erase the scratch work because we don't need that anymore. So I want to show a few more short examples right now just to demonstrate the idea. Um, let's try another one right here. We have f of x to, let's say, the square root, right? Now again, this one, just like the green example, it's not in the right form. We want x to some exponent, and it's nice that we can actually turn the square root of x into x to the 1 over 2. And now, when we want to find its antiderivative, what do we get here? That's going to be what? Now leave some space, and then x to the, if you are adding 1 to the 1 over 2, that's going to give us what? 3 over 2, right? So 1 over 2 plus 1 is 1 over 2 plus 2 over 2, because we need to get the common denominator. So we get 3 over 2, right? So 3 over 2. Okay. Now, again, we need to multiply by some number in the front, right? What is that number? That number would be the reciprocal of our new power. So what is the reciprocal of 3 over 2? It's going to be 2 over 3. Let me write the 2 better. Okay, so that's too bad. Let me write it one more time. 2 over 3. And then plus the constant c. Okay, let me just show one more example. Let me just show one more example right here. Then what are we going to get here? So let's say if I have just one. This one looks a little bit weird because it doesn't even look like a power function. We have just one, right? But actually, we can also write it as a power function. We can write it as 1 times x to the 0 power. Okay, so how do we get 1 times x to the 0 power? I mean, what is its antiderivative? It's going to be what? It's going to be, again, as long as the exponent is not going to be what? It's not going to, it's, if it's not like the 1, then we are going to get what? We are going to be able to apply this formula. So add 1 to it, which becomes a 1. 0 plus 1 is 1. And then when we multiply by the reciprocal of 1, which is just 1, and then of course, if we simplify that, then we are going to just get x. So now, if you take the derivative of x, we are going to get what? We're just going to get 1. So that's simple. Okay, so that's those are 4 really common examples that we usually would see, and when we are finding the antiderivatives involving power functions, it's usually a mix of those ones. But you can only use this formula if the function is x to some power. Yeah. So it's wrong. Let me show you how to do the problem wrong. So make sure that you don't do this. You can do it wrong like this. So how do you do it wrong? It's this. Let's say we have a function, okay? And that's 1 over x to the 1 over 3. Okay, so you know that to do it correctly, then we actually need to bring it up to the top so that it will be x to some power. In that case, it would actually be x to the negative 1 over 3. But then instead of doing that, then it will be wrong if you just do it in the denominator. So if you add 1 to the 1 over 3, then you get 4 over 3, and then 3 over 4 in the front, and then you put the plus c. So that will be wrong. Yeah, so make sure you don't do that, right? Always write it as x to some power before you apply the formula. Okay, now let's look at the case when n is equal to negative 1 and see what's going on. So let me just point out one thing here. When n is equal to negative 1, then there is only just one function. That function is x to the negative first power. And if you write it without the negative exponent, it's actually 1 over x. And then if we want to find the general antiderivative of this 1 over x, how do we do that? Let me just recall something right here. Let me just recall something here. So when we take the derivative of ln of x, what are we going to get? We are going to get 1 over x. And then that's, of course, that's going to be assuming that x is positive, right? That's going to be positive. And then now what about, there is another one that we know that will also give us the same function when we take its derivative. And that function would just be ln of absolute value of x. When we do that, then we are going to get the derivative as 1 over x. You see that we actually will get the same 1 over x right here, and we want to find the antiderivative of 1 over x. Which ones do we pick here? Now, one more thing here, we should mention the domain for the ln of absolute value of x. Because we are putting the absolute value around the x, so we allow x to be a negative number, but of course we still can allow x to be 0, so we can actually have any x value except 0. So now what happens? Which ones do we pick? Should we pick ln of x because it looks simple because there is no absolute value, or should we put ln of absolute value of x? We actually should be putting this one because if you just think about this, in the original function, we didn't even specify the domain right here. We actually allow x to be any numbers except 0 in this case. So to actually find an antiderivative with the same domain, we actually should be picking the ln of absolute value x. So our antiderivative for 1 over x would be ln of, which is the natural log of absolute value of x, and then plus the constant. Okay, so that's how we can get that. Now, this will cover all the cases that we have here. So for the first one, then we actually have what, x to the n, and when n is not negative 1, then we can actually reverse the general power rule by using this formula right here. But when n is equal to negative 1, what happens? Then we have 1 over x. When we have 1 over x, its antiderivative would be natural log of absolute value of x. And so that's it for these two problems. It's actually just one problem with two different cases. And so if